This is second part of the problem solving session of week 8. So we continue with Newton's method. Let me recall it before we start solving the next problem. Okay, recall about Newton's method. Okay, so Newton's method is all about approximating the roots of a given function. Newton's method. So it gives us approximations on the roots step by step by the following recursive formula. Xn minus fxn minus fxn divided by f prime of xn. Okay, this formula comes from the tangent lines drawn to your curves at the approximated points after another. So I explained where does this formula come from in the lecture video. You can go to there and listen to the detailed explanation where this formula come from. But as I can say in short, that this formula comes from the equation of the tangent line drawn to your curve from the roots or from the approximations that is obtained at each single step. And in this formula, as you can see, since we are dividing with this expression f prime, we require that it is non-zero, obviously. This should be assumed. And to be able to start this approximation process for approximating the roots at each step, you need to choose a nice initial first guess, okay? Choose a nice initial guess to start the process, let's say. Okay, I explained all those details in the lecture video. You can go there if you don't remember. Okay, let's try to solve this exercise by using the ideas that we covered about Newton's technique. For each initial approximation, determine graphically what happens if Newton's method is used for the function whose graph is shown. So we will try to understand whether the given initial points are nice ones to obtain a nice approximation for the roots of the function by using Newton's method. Okay, consider x equals 0, x1 equals 0. Let's choose this as the first initial guess. Then does the method works? Let's see. Okay, so x equals 0 is here. By the way, this is the graph of y equals f of x, and you can see the roots of this graph, roots of this function, right? One of the root is 2 and the other root is seen as 6 from the graph. And we try to understand here. Let's pretend like we don't know the roots and we are trying to approximate them by using Newton's technique. And the question is, if you start applying Newton's technique with this initial guess where x1 is 0, then does it work? There is a geometrical way of understanding if the technique is working or not. Here is how you can check that. You start drawing tangent lines step after one another for each step, and you will check whether the x-intercepts of those tangent lines are approaching towards the actual root or not. If those x-intercepts of those drawn tangent lines are approaching to the actual roots, to one of the actual roots, then this means that Newton's method is working. Okay, let's check it. x1 equals 0 is our initial guess, initial point to start. And what I will do is, what I'm going to do here is, I will draw a tangent line right at this point, x1 equals 0. You see, this is our tangent line, and I am sorry about my drawing. It should be more like a straight line like this. Okay, this is the first tangent line and it intersects the x-axis at this point. And next, you will keep doing this. You will draw another tangent line to the curve at the second point. Okay, this is x2, then I will draw a tangent line to the curve again at this point, x2. Something like this, right? And its x-intercept point is here, and then keep drawing tangent lines. You know, this is your curve, and now I am here. Third x-intercept is x3 is here, and then I will draw one more tangent line from x3. You see, the lines are getting more approaching to the horizontal line more and more at each step, and then this is enough to conclude that, to see that those x-intercepts, and this will be the next x-intercept of the current tangent line. So you see that x1 was here, then we moved to here, to x3, to x4. X-intercepts of the tangent lines are not approaching to one of the roots, which are 2 and 6. They are, in fact, they are getting far away from the roots, which means that this initial guess was not a nice one. And for x1 equals 0, this initial point, Newton's method is not working, as we can see that x-intercepts of recursive tangent lines are not approaching to the actual root. They are getting far away. Okay, let me write the explanation. This initial point is not a nice guess to start Newton's method. Because, what is the explanation? Because as seen from the picture, the x-intercepts, those x-intercepts are called approximations. X-intercepts, in fact, given approximations by the method, are not getting closer to the actual root. That's why Newton's method is not working for this initial choice. Okay, this is the explanation. This initial choice was x1 equals 0, and we see that the Newton's method is not working for it. As you can see, the approximations are getting not closer but far away from the actual roots. Let's try the next one, B. Let's try x1 equals 5. 5? No, sorry, 1. Okay, now I will start the same process for this initial choice, which is x1 equals 5, draw a tangent line. You see, I need to draw a horizontal tangent line for x1 equals 1. At the first step, the tangent line is horizontal. There is no x-intercept, meaning that there is no next approximation. You see, what is wrong with this initial choice is the following. For x1 equals 1, the first derivative at 1, which is the slope of the tangent line, is in fact 0, which is forbidden in the process, right? Which is not a valid starting point. Since this happens, Newton's method again does not work for this initial choice too. Because if the first derivative, as you can see, if the tangent line is horizontal there, first derivative at that point is 0, then the denominator becomes 0, which makes the process undefined. Okay, let's try the next one. Let's try x1 equals 3, see what happens then. Again, we will try to understand by drawing tangent lines recursively after one another. Okay, x1 equals 3. We take this as the initial guess, as the initial point. The first tangent line will look like this one. Right, I'm sorry. There is a problem about my drawing of tangent lines. Okay, you see x-intercept is here. Let's call it as x2. Then what I should do is I need to draw another tangent line at x equals to the curve. I draw it like that. And then next intercept, let's call it as x3. And it is here. And keep doing the same process. Let's draw one more. Go to the curve and draw another tangent line there. And this point is then will be x4. You see, I get really close. I start getting closer and closer to the actual root, which is 2 at each step. The x-intercepts of the tangent lines, when we start x1 as 3, then x2 is here, and x3 is here, and the next x4 is here. They are getting closer and closer to the actual root, which means that Newton's method is working perfectly for this initial choice. The explanation is the x-intercepts of tangent lines drawn to the given curve are getting closer to the actual root, which is 2. So Newton's method works perfectly for this initial choice. For this initial choice, okay? So that's how you can check whether the Newton's method is working or not for this given initial choices. For x equals 4 here, I think the situation is the same as for x1 equals 1. The horizontal tangent line, so the first derivative is 0. Newton's method does not work for x1 equals 4. For x equals 5, the situation will again be similar to this case when x1 equals 3. You can understand it will be working when you draw tangent lines after one another. And you observe that the x-intercepts of those tangent lines are getting closer to the actual root, which is 6 in this case. Okay, that's how you work Newton's method geometrically. Let's move on to the next example. This time we will work algebraically the Newton's method. Okay, the question is, how many solutions does this equation have? Use Newton's method to find them. Find here is a strong word. I guess we should change it with approximate. To approximate. Okay, look at your equation. You know, we can apply Newton's method to a curve, not in the form as an equation. So we need to transform this equation to a function. Like f of x is sine 2x minus this number plus 2x squared. Okay, this is our function on which we can apply Newton's method. In fact, we have two curves here, right? One of them is sine x, the other curve is this one. And if you try to solve an equation like this, and you can, if you want to consider the solution of this equation geometrically, it will be in fact the intersection points of these two curves, right? So let's try to draw both of them in the same coordinate axis. Okay, sine function is a periodic function which does this oscillation, sine 2x. You know, normally sine function does this behavior. If you multiply with x, you just change the period of it, but its oscillating behavior won't change. That's why I will just draw it like an oscillating graph like that. Let me draw it smaller. Maybe, okay. Oh, yeah, this looks better. So this is y equals sine 2x graph. What about this one? Okay. This one, y equals 0.22 minus 2x squared. You can draw this one by using shifting. It is a parabola, in fact. Okay, you know, this is y equals 2x squared, a parabola. If you reverse it with respect to x-axis, you will obtain y equals minus 2x squared. And then if you, by adding this number, what you do to the graph, you just move your graph this much unit up to obtain it. Like this, by shifting, you will obtain such a parabola. Let's insert that parabola to our picture. Okay, so it is that kind of parabola, I guess. So like this. Okay, this is 0.22. And as you can see, the blue parabola, which is the curve y equals, okay, let me just remove this part where I explained how to shape graphs. So this blue curve is this parabola given in the statement, 0.22 minus 2x squared. And solving this equation together means that you are in fact solving the intersection points of these two curves, right? And as you can see, there are two intersection points of these two curves. That's why this, okay, let me say two intersection points. Points means that the given equation has two solutions. Sine 2x equals minus 2x squared has two solutions, okay? Finding intersection points means that you need to solve those equations together. So this, if you solve these equations, if you find the roots of these equations, there will be two, like this one, first root, and like this one, the second root. Let's call them as R1 and R2, root 1 and root 2. Okay, so we prove that there are two solutions of this, exactly two solutions of this equation. Geometrically, we prove that there are two solutions. So that's why I can write 2 here after this geometric solution. Now, we will approximate these two roots, these two solutions, by using Newton's method. Okay, let's start by approximating root 1. Okay, Newton's method now. Method. We are approximating root 1. Approximate root 1. Okay. So, as I said before, we will be using Newton's method, not geometrically, but algebraically this time. So this is the given formula. And so I will start applying this formula for consecutive consecutive integers n. So if you insert n equals 0, what do you obtain? You obtain formula like that. And then now you need to choose a first nice initial point. What is x0 here? So this will be your first guess. Okay? First guess, and you need to guess it by yourself. Let's choose the initial point as 0. Why I am choosing it as 0 because, as we can see from the picture, root 1 and root 2 seem to be closer, seem to be close to the origin point, right? That's why let's choose the first guess as 0. You will choose this initial point by yourself to start applying this formula algebraically. And then what you have from the formula is this one, okay? So now you need calculators to compute f of 0. What is your function f? F of x is, as we write here, sine 2x minus this number plus 2x squared. You can easily insert 0 to this function so that you obtain just this coefficient given here. And then you can compute the first derivative function easily. Okay, let's compute it. Derivative of sine is cosine, and then you need to multiply it with the derivative of the insider part, which is 2 plus 4x. This is first derivative function. You can easily insert 0 to this function. So this is 0. That's why the result, by the way, sorry, I guess cosine 0 is 0. Cosine 0 is 1, so you will just obtain 2 for the first derivative. So it is 0.11. Okay, then you keep doing such computations for the next integer numbers like n equals 1. So insert n equals 1. You will find this formula coming from Newton's method. Okay, now you will insert whatever you find in the previous step for x1. x1 is computed as this number. So just insert it, 0.11. f 0.11, f prime 0.11. By using calculators, you can find the value of this. Let me write the value that I found by using my calculator. I found the value like that. And if you keep applying this process for the next steps, you will find x3, the third approximation, as 0.100564. And the next approximation, fourth level approximation, will be 0.1164. So they will just differ at the digits, like these digits after the comma. So they are really close numbers to each other. So you can stop here. You can stop the process at any step you like. So let me stop here and let me take the root as this number. Okay, the fourth approximation, I stop the process here, will be our approximation to the root 1. Okay, for root 1. Okay, so it is 0.1 blah blah something, and as you can see, the 0.1 is kind of, this root is close to the origin, and it is proved by Newton's method by computing this approximation like that. Okay, these are our approximations. x1 is found like this, x2 is like that, x3, x4, and I stop the process here as I feel like we are getting really close to the actual root. Now you can do the same process for root 2. Let's also compute some values, some approximations for root 2. Okay, we will be using the same procedure, and you need to choose an initial guess. Let's choose this time the initial guess as minus pi over 2. Why I am choosing like that? Because second root is a negative number, and again you need to choose some point closer to the origin. That's why I prefer to choose it like that. And by using this number, if you apply the formulas coming from Newton's method like this, like the one we did above, you will find these values. x1 will be computed as minus 1.00159. By using x1, you can find the value of x2 as minus 0.820.269. X3 is computed by using the Newton's formula like this one, 2814, and X4 is 78. You see the first digit becomes the same, the next digits are changing, and they are again getting closer to the origin point. So I will stop the process here and take this as the approximation for root 2. Okay, you can stop the process anywhere you like. Okay, this is how you apply Newton's technique algebraically, as we did in this question, and geometrically, as I explained here. So I move on to the next part. The last question is about antiderivatives, okay? This is about antiderivatives. Okay, and this is somehow related to the integral, which is the title of our next topic. We will start the integral chapter next week. Okay, let's concentrate on the statement now. The graph below shows solution curves of the differential equation. Find an equation for the curve that passes through the labeled point. Can you see the labeled point? Okay, let me zoom in. This is the labeled point, and the solution of this differential equation will be the function y itself. And once we solve it by using antiderivatives, you will see that there will be an arbitrary constant in the solution. Because of this arbitrary constant, we will draw lots of lines depending on the value of that arbitrary constant. Let me exemplify that with a simple exercise. So this is the graph of y equals x squared curve, x squared parabola. And for example, if I take it some units below, this will be the equation will look like that. If you take it some units up, the equation will be like this. And you can also draw many other lines. And in general, you can express the equations of all those curves, like putting an arbitrary constant for +1, -1, and there will be other constants for some other curves drawn upwards and drawn downwards like that. So arbitrary constant C tells you that you can choose any real value for C. For each real value of C, you will draw another curve like that. That's why you obtain a family of curves like this one. Okay, so now let's try to solve this differential equation. Taking derivative and antiderivative are inverse operations, okay? Let me put a recall about that. Recall. X to the power n, let's work with this power function. X to the power n, let's take the, let's consider the antiderivative of it. Antiderivatives of power functions and some other several functions are explained in the recorded lecture video. Antiderivative is in fact the reverse of the operation taking derivative. So they are inverse operations. So to find the antiderivative of x to the power n, we need to consider in the reverse order. You will consider like what should be the function whose derivative is x to the power n, right? While taking the derivative, you are subtracting 1 from the power, right? So that's why if you start with x to the power n plus 1, after taking one derivative, the power should be decreased by 1 and you will obtain x to the power n. But then you will have some extra coefficient like this in front. To get rid of it, you can put 1 over n plus 1 in front, okay? That's why the antiderivative of x to the power n, the power function where n is any real number, the antiderivative of it, by the way, it is not any real number, of course, because of this denominator where n is different than -1. The antiderivative function look like that. Now you can verify by taking the derivative of this expression. You can verify that its derivative is given like this. Okay, then go back to our example. We can also work with constants. What is the antiderivative of 1? What do you think? What should be the antiderivative of 1? Can you guess a function whose derivative is 1? Obviously, it is x, right? So if you take the derivative of x, you will obtain 1. So the antiderivative of 1 should be x. Okay, 1, if you take the antiderivative, you will obtain x. Now we are taking antiderivatives. Okay, you have a power function here. The constants survive there. And what is the antiderivative of x to the power? 1/3. And we just covered the general rule here. You will add 1 to the power and you will divide by the same power. Again, minus n plus 1 given in this expression. 4/3 should be also written to the denominator. Okay, maybe I should write it in a more clear form. What I did here is the original power was 1/3 and I added 1 to the power as the rule tells me, and I divided with the same power. And then, okay, so what we obtain for the y function was 4/3. And what we have here is 4/3. By the way, I guess we have 4/3s everywhere, so you can simplify it. These two are gone. And be careful. You should add an arbitrary constant c to your original function y, because if you take the derivative, and you can verify that, if you take the derivative back, this arbitrary constant will be gone, right? So that you will obtain the first derivative exactly like this. So there should be an arbitrary constant at the end. And we call this as the general form of the antiderivative function, the most general form. And, there is a detail in the statement, like our curve will pass through this point. And by using this information now, you can easily solve for c. So let's use our information to solve for the arbitrary constant c at the end. Okay, so we solve the original function as x to the power 4/3 plus c. And we know that our curve passes through the point x equals 1 and y equals 0.5. Let's insert these points. Y equals 0.5, x equals 1. 1 to the 4 plus c. You see from this equation, c can be solved as 0.5, or let's say 1/2. 1/2, of course. Then you can find the original function by also solving for the arbitrary constant c. It is given as this one. Y equals x minus x to the power this, plus 1/2, which is solved for the arbitrary constant c, okay? This is the solution of the differential equation given by this expression, and that passes through this point given in the picture. So that's it. Thank you for your attention.